This is a lesson on inequalities with linear functions and their graphs in Precalculus. I wanted to start with a quick review about inequalities, linear inequalities. And by this point in your math curriculum, I expect you to know this material. Inequality and interval notation, we've been talking about that with domain and range, so you should be able to use these notations well. As we're looking at graphs of linear inequalities, I need you to know about closed dots and open dots, or square brackets or parentheses, where we have some sort of indicator where values can be included into the range with the equal sign in here. So that would be a bracket. Or a closed dot. A closed dot would also include that value, as opposed to an open dot or a parenthesis where that means the value isn't included. So also, if I wanted to write out the expression, for instance, this down here, this interval down here, I'm going to note that it can equal -1 and it goes up to infinity. No value ever equals infinity, so it can't be an equal sign here. It has to be a less than sign. This isn't the proper way to write this. Remember, if there's an infinity involved with an inequality, we're just going to go x is greater than or equal to -1. And with interval notation, we would say -1 comma infinity with a parenthesis on the end. So just a little review there. We're going to move this into 2-dimension, but I want to ground in what you already know about solving linear inequalities in one variable. We're going to move to 2 variables here in a second, but you already know about one variable linear equalities, hopefully. I'm going to remind you also of the inequality algebra rule. If multiplying or dividing by a negative with an inequality equation, the direction of the inequality changes. So for instance, if I have -2x is less than or equal to 4, if I divide by -2 on both sides, I'll get x is greater than or equal to -2. You see, because I divided by that negative sign, then the sign, the inequality changes direction. So that's what that is. When we solve simple inequalities in general, we're just going to get some region on the graph, right? This line graph. Just some region is true and it has some values that can be included that solve that simple inequality. But then you moved on to compound equalities, where more than one portion of a number line may be the solution. So you solve one equation and you solve another equation, and there may be an and or there may be an or situation. So this would be an and situation, where you want a value that solves both this f and this g, and so that would be down here. F can take on all of these values, g can take on all of these values, and if you want the solution set that fits both f and g, you have to choose that last option on the number line. If you have an or situation, it could be it solves f or it solves g, and so you give 2 intervals on the number line. So you can see how those are more complicated than just a simple inequality. We're considering 2 different things being true, and are we combining them, or it's a separate thing? So those are what we call compound inequalities. So let's look at that stuff in the context of linear functions in 2 variables, where we have not only an x value, but also that y value going on. And so what we're looking for is output values that satisfy a condition on the linear function. Okay, I have a couple of examples here, and I'm going to walk through them on this graph. The first thing I did was just graph a line. Do you all see that black line on there? That's just an equal sign, and it's just a line. Okay, it's denoted with a solid line, and there's no shading associated with it, because that's what it equals. There's an equal sign, and an equal sign has a solid line. Okay, I plotted the blue line here and shaded it. So this is an inequality. It's not just a line, it's an inequality. It's an inequality with a line. So it's the blue region. What I'm going to note, and I mentioned this on the previous slide, there's no equal sign. It's a greater than, and when we're using greater than or less than, When it can't equal that value, we're going to use a dotted line. And you all can see on here that there's a dotted line for the blue inequality. There's a dotted line, and that corresponds to that greater than sign. Another thing that we're doing is we're shading the graph. So you can see where the blue is shaded here. I'm going to shade in blue again. All of the values of y that are greater than this line, we're going to denote with shading that region above the line. All right, it's greater than that line. If it was less than the line, we would shade under the line. But because it's greater than the line, we're going to shade over the line. So that's how we represent that inequality on a graph with a line. Okay. The other one down here is another line. It's the other line on there, and it's the red one. Notice that it has a less than or equal sign. So because it has that equal sign in there, we're going to draw it as a solid line. So you can see on the graph over here that we have a solid line on this second inequality. And that's the graph of that line. We want it less than, so any value that's less than, we're going to go below the line. If it was greater than, it'd be above the line, but we're below the line. So hopefully it makes sense above the line and below the line. There may be situations where you're not sure if it's above the line or below the line. The one that's really like coming to my mind right now is if a line just looks like that, but then you just say like x is greater than -3 or less than -3, right? So if it's greater than -3, it would be this region of the graph. There's not really an up or down, right? But you shade the region where that is true. Compound inequalities. Let's talk about compound inequalities. Compound inequalities, I mentioned, was when two things are true. So they'll denote this. You'll see this large bracket to the side. And so that means that both of these need to be true at the same time. And I'm going to interpret this as an and situation. During what part of the graph is this true and this true? So you can see it's not the blue area and the red area. It's the blue area where it crosses over the red area. This is the solution set that solves both the first inequality and the second inequality. That's the solution set for both of them. That would be an and. If it was an or situation, and I don't think you see this maybe in your homework, I could be wrong. If it was an or situation, I would shade all of this. It would be all of that would be true. It would solve this one or that one. All of those values solve this one or that one. But that purple area is the and. It solves this one and that one. And so this is Precalculus. You're learning how to use graphs more. Always graph to visually inspect and verify the solution. I have a situation where with the graph and how I want you to draw these graphs, how I want you to make sure when you present them to me, what I'm looking for and how to graph them properly. So what I have here is a simple linear function inequality. All right. What we're going to do is we're going to take these two functions, given these two functions, and one's a little bit weird form, but that's okay. We can work with it. Solve the inequality when f is greater than or equal to g. Okay. And write your answer in interval notation. Of course, we're going to write it in interval notation, and we're going to look at the graph. That's what I was just talking about a second ago. All right. So let me write this out. I don't think this is going to scare anyone when you look at this. If you're comfortable with solving simple linear inequalities, we're going to get the one function, and we're going to set it greater than or equal to the other function. That's it. I'm going to tell you if and when you plug this into the Desmos or any other graphing program, that's what it's going to give you. That is not the proper graph for this function. This is not correct at all. If you see this, if I see this, I am going to put a big sad face on it because that is not the proper graph for this. What you need to do is graph each one of these separately. All right, and then find the area where this is true, where this statement is true. Okay, so We know the answer here. You can solve for it algebraically. We can solve for it algebraically. 26x plus 18 equals 15 plus 7x. I'm going to subtract this to this side and this to this side. So I get what? 19x equals negative 3 and x equals negative 3/19. So if you were asked for a fraction for an answer, you'd be able to put, I assume that's what the 0.1577895 value is. Whatever that, right? Negative 0.1577895. That's what that is. But let's graph it properly. I want you to graph it properly. Also, let's do this first. It says, where is f of x greater than g of x? I lost my greater than sign, didn't I? Greater than or equal, greater than or equal. I divide by a positive sign, I still get a greater than or equal. And so that's what you see on this. This is greater than or equal that value, right? That's what Desmos told me where x is, that's true. But what I'm looking for, this is what I'm saying about what I'm looking for on graphs, is that I want you to graph each one of these functions separately. All right, so when I look at this, they both have a positive slope. One's steeper than the other. So let's see, which one is f? It has an intercept of positive 18. Remember, it has an intercept of positive 18. So f must be the red one. This is f of x and this is g of x. Those are my two functions. And what it's asking is, when is f of x greater, when is the output of f of x greater than the output of g of x? So when I follow f along here, I see that f is below, the output of f is below g of x. I still have a below. Here they intersect. And in this region, this is where the value of f of x is, the output is larger than the value of the output for g of x. So when I shade this, technically this is how I would do it. Here's this value that we calculated in here. Okay, I need to erase this. I'll get rid of our little smiley sign. I hate that those pop up. I don't know why that happens. Okay, so this is how I would shade it. In this region, there it is. Okay, I wouldn't necessarily shade up here because I'm not interested in those values up there. That's why I would shade only up to that line. And I think that's a little different than if you did it in Desmos. I think it would shade this region. I guess maybe I'm arbitrary because Desmos does it, but Desmos is wrong sometimes when they do things. For me, when I see this, as I teach this and see this in textbooks, don't shade above that upper function. And notice that this graph is way different than this graph down here that I did to begin with. That is not the correct graph. What you need is this graph where you have the two lines on it and you're shading the region that satisfies the inequality. I picked out another example problem that I see students struggle with. This is a compound. You can see that I have this bracket here so that it combines these two. This means an and, right? In what region of the graph is this true and this true? Well, I like this problem because they give you the two graphs. All right, less than, it seems like this is the blue purple down here is the top one. Yeah, it has a negative slope, and the red one here is the bottom one. It has a positive slope. And we can also tell because this has an equal sign, and that's the solid line over here. So we can see in here, this is the region in which the values of the output satisfy those two inequalities, okay? So it says, for these points, consider the following system of equations: which ordered pairs shown are solutions to the system and which are not. Well, what we can do is we can just look at the graph and see where the point is, and is it within that region, all right? So negative 4, 6, so negative 4, 6, it's on the line. I know if I have a solid line, that's included in the solution set, so I can say yes on that one. Negative 3 comma 3, I can see that is, negative 3 comma negative 3. Let's get that right. Read carefully. Okay, you just saw me do that. Watch little mistakes. Read carefully. I'm going to see that point is on the dotted line. And I'm going to remember with dotted lines, it cannot equal that value. So I'm going to say that negative 3 is not a solution. So all these points are going to be either a solution or not a solution. If it's not a solution, then it has to be, if it's not a solution, it has to be a not a solution, okay? So 5 comma 6, where's 5 comma 6? That's definitely, it solves one of them, but it doesn't solve both of them. We need this point to solve both of those inequalities. So this is a no as well. Negative 3, 1, negative 3 comma 1, that lies in my region, yes. 4 comma 6, 4 comma 6, another 6, here we go, 4 comma 6, that's outside, I'm going to say no. 6 comma 2, 6 comma 2, there's 6 comma, 6 comma negative 2, 6 comma negative 2. Okay, so it looks like it might be, it definitely solves the top inequality, but it doesn't solve both of them. So that's outside. And the last one, here we go, easy, easy, is the origin. It's within the solution set. Okay, so that's how you do a problem like that and reading the graph. I picked out a few more problems, just 2 more. They're application problems in context. So again, working with word problems and translating word problems into equations to be able to solve them. Not only do you graph them, but you have to solve them. Eric won 42 Tootsie Rolls playing balloon pop at the school fair. He gave 2 to every student in his math class. A little grammatical error there. He has at least 6 left. Okay, so at least, that's what's going to tell me that this is an inequality. When I see at least, no more than, maximum, minimum, blah, 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 right? We have a maximum here. Write and solve an inequality for the maximum number of students in a class so that he can share his candies with everyone. What a nice guy Eric is. Okay, so we need to translate this into an inequality. What I do not want to see you doing is start writing out numbers and then reverse engineer an equation or just, what I need to see is an algebraic solution. All right, not just a numerical solution. You can get an answer guessing numbers. You can do that, but that's not what I want. I want you to show me that you can use algebra and inequalities to solve this problem. So if I write out an algebraic problem, let's see. We need a number of maximum number of students. So why don't I make S the number of students? So when I think about Eric handing out his candies, he's going to start with 42 of them. And he's going to give away 2 for each student. So that's why I have a minus in here. He's giving away 2 for each student. So negative 2s. And when he gets done with that, he's going to have at least 6 left. So that's going to be greater than or equal to 6. And so this gives me my algebraic equation. Now I can, or any algebraic inequality. Now I can solve for s. Let's solve for s. I'm going to move this over to this side and that over to this side. So 42 minus 6 is 36 is greater than or equal to 2s. I'm going to divide by 2 on both sides. Divide by 2, divide by 2. 18 is greater than or equal to s. So s, the number of students, has to be less than or equal to 18 students. So there can be 18 students in his class, and he can still have at least 6 left, maybe for himself at home or whatever. Because he did win it. That was his win. I didn't do a graph for this one. There's not 2 variables, so I didn't feel comfortable putting it on Cartesian coordinates. That didn't make sense to me. I suppose if you were going to graph this, you might do it just on a number line, right? both directions. S is greater than or equal to 18. Here's 0, here's 18. It can equal 18, and then I would just shade like that. So that is maybe a review problem, but I know people can still struggle setting up an inequality to solve, and I see students struggle with the problems in this lesson that pertain to that. So I wanted to cover it. Let's do another one that's very similar to this. It's going to have one variable, and so we're still practicing writing out equations and inequalities from words. We have sides of a triangle. One side of a triangle is 17 centimeters shorter than the base x. Okay, let me do this. We have a base x, and we have a short side and a long side. One side of the triangle is 17 centimeters shorter than the base x. So there's the base x, and I'm going to call this one side x minus 17 because it says shorter. The other side is 18 longer than the base, so 18 centimeters longer. So I'm going to go x plus 18. What's the length of the base that will allow the perimeter of the triangle to be at least 40 centimeters? So that's how I know that this is an inequality, because it has the word at least in here. I know the perimeter is, if I add all the sides together, I can generalize this for any object, but I have just sides here of a triangle. So I'm going to take all three of them and say a perimeter is x plus x minus 17 plus x plus 18. So when I look at the perimeter, I'm going to have the equation 3x plus 1. What this situation is specifically telling me is that has to be at least 40 centimeters. So I can say 3x plus 1 is greater than or equal to 40 centimeters. So I can solve for x in here. This isn't too bad. X is greater than or equal to 13 centimeters. Please remember that physical quantities have units on them. I will be watching and marking for students to put physical quantities on, or units on their physical quantities, so make sure you put a centimeter